This section is about forces and motion. If an object is at rest on a table or hanging from a thread, it will stay where it is. That sounds obvious, but the reason is because the forces acting on it are balanced. The weight of the book acting downwards is balanced by the equal and opposite force of the table pushing upwards. The weight of the ball acting downwards is balanced by the equal and opposite force of the thread pulling upwards. This is part of Newton's first law of motion. This says that if the forces working on an object are balanced, it will remain stationary or will continue to move in the same direction. That second part is more difficult to believe. We know that a toy car rolled along the floor doesn't continue to move forever. So is Newton wrong? Think about it as you watch this clip about the space shuttle.
Small adjustments to the height of the orbit and the position in the orbit can be made using small thrusters. To the astronauts, free falling with the ship, it seems that when a thruster is fired, the shuttle moves off in the opposite direction and continues moving until an opposite thruster is fired.
Okay, rod release, ready, green, 33. Helmet lights on, helmet lights are on, and your bumper.
To get to the satellite and to make small changes to it, the astronaut had the MMU, the Manned Maneuvering Unit. "300 meters can be a long way in space. The MMU is maneuvered by very tiny thrusters, but in the same way as the shuttle.
Okay, Pink is sitting out there at about 140 feet at this time. Sure.
He had no sensation of hurtling round in orbit. He felt as if he was floating weightless and using the MMU to move around.
You're looking good there, Pink.
Still, the astronaut had to use the thrusters gently. Too much or in the wrong direction, and he would have pushed himself dangerously off course. The idea was for him to match the spin of the satellite, then clamp on and use the thrusters in the opposite direction and so stop the satellite spinning. At least that was the theory. In fact, because his mass was low and the much more massive satellite was turning quite quickly, he was knocked away.
You might have noticed that, floating in space, the shuttle and the astronaut did keep moving until they used their thruster rocket to stop the movement. Also, we saw that the satellite would keep on spinning until the astronaut managed to stop it. So Newton was right. On Earth, there are many forces acting on an object. Friction is a force that opposes motion and reduces the speed of a moving object. Friction takes place between the objects and a surface. The rougher the surface, the greater the friction. Friction increases with the weight of the object. Air resistance, also called drag, is the way that air resists an object that's trying to move through it. The shape of an object affects its air resistance. The more streamlined the shape, the lower its air resistance. Contact forces are when two objects are in contact and exert an equal and opposite force on each other. Gravity is the force on any mass pulling it towards the centre of the Earth. The force of gravity on an object is its weight. On Earth, gravity exerts a force of around 10 newtons on a 1 kilogram mass. Gravity is a field force. It works without being in contact with the object. In your exam, there's a proper way to represent forces. You use an arrow pointing in the direction in which the force is acting. The length of the arrow indicates the size of the force, while the head of the arrow indicates its direction. For the object to stay still or to keep moving at constant speed, it needs all the forces on it to be balanced. What are the forces on this stationary car? There's the force of gravity acting downwards on the mass of the car, its weight, which is balanced by the upthrust force of the road surface on the car tyres, which pass through the car's suspension to hold up the mass of the car. The car is now moving at a constant speed along a flat and level road. What are the balance forces on the car now? You should have got something like this. There's still the force of gravity acting downwards on the mass of the car, balanced by the upthrust force of the road. But now the car is moving at constant speed. There's also the forward driving force provided by the engine passing through the wheels and tyres to the road. This is balanced by the frictional forces in the turning wheels and where the tyres meet the road, as well as the drag from air resistance, both trying to slow the car down. If there were no drag or friction and the road stayed flat and level, what would happen if the driver switched off the car engine? According to Newton's first law of motion, if there were no drag or friction and the road stayed flat and level, the car would continue rolling at the same speed, forever, just like a space astronaut. What if the forces on an object are unbalanced? If the forces acting on an object are unbalanced, the object will start to move and speed up or slow down and stop. Watch the next clip to see how much force is needed to get an object moving and how much force is needed to stop it.
This is an old-fashioned horse-drawn dray, and it's still used to deliver beer in London. It has a mass of 1,500 kilograms and normally takes 2 strapping shire horses to pull it around. But today, it's just going to be Jamie.
Ready, Jamie? Go!
Now, if I convert the reading on the forceometer into metric units, I can see that Jamie needed a force of 4.5 kilonewtons. That's 4,500 newtons to start the carriage moving, but he doesn't seem to need as much to keep it moving.
Stop!
But how much force would he need to stop it?
Jamie, awesome or what? Amazing. Now, you obviously had to exert an awful lot of force to get the carriage started.
It's always difficult starting something like this because you have to overcome friction and unbalance the forces, but once it's actually moving, it's just a constant force to keep it moving.
So to get the dray to move, Jamie had to unbalance the forces acting on it. As it starts to move, it's accelerating, or rather being accelerated by Jamie pulling with a force greater than friction. But once the carriage was moving, it became a lot easier because all he had to do to keep a constant speed was to balance the forces acting on the dray. But to slow down and stop the carriage once again required unbalanced forces.
You need an unbalanced force to make something accelerate or decelerate. In fact, if you double the force, you double the acceleration. If you double the load, that's the mass, you halve the acceleration. The bigger the unbalanced force, the bigger the acceleration. The bigger the mass, the smaller the acceleration. Let's summarise. Forces have a size and a direction. Forces acting on an object can change its shape, make it start or stop moving, make it speed up or slow down, or change its direction. The bigger the force, the bigger the change. The bigger the mass, the bigger the force needed to bring about a change. Static objects can exert a force. If an object is either at rest or moving at a constant speed, then the forces acting on it are balanced. If an object starts to move, speed up or slow down, the forces acting on it are unbalanced. There's more about forces and motion in the higher tier programme. That's the end of the section on forces and motion.